Welcome to this lecture series of multivariate calculus. In this lecture, I will talk about the Jacobian. Okay, yeah. So let's us see what is the Jacobian and what is the application of the Jacobian. So, so let us start with this Jacobian by taking some example. So it's Jacobian. Okay. So suppose in the one variable integration, so means that what integration right? So suppose there is one integration of some function, let's say fx and dx. Okay, uh, sometimes it is easier if you change this variable. If you put some, let's say, y equal to, let's say, x square or x equal to root y, then if you do this change of variable, then during this integration it will be very helpful. You can easily evaluate this sort of integration. Sometimes it's happened that we need to change the variable, right, for the single variable case. Suppose if you have two variable, means suppose you want to find out this sort of thing, integration of fxy. So fxy is a surface, right? And so it has two increment dx and dy, two direction, right? So during this change of this variable for this double variable data, we need to find out the Jacobian. Suppose we are changing this Cartesian coordinate to the two-dimensional polar coordinate by transforming x equal to r cos theta, y equal to r sin theta, then at that time use Jacobian is required, right? How to find the Jacobian? We'll see later. Also similarly, in the case of, let's say, you have triple integral. So triple integral basically represent the volume. Okay, so sorry for this the symbol of the integration. So this is suppose the triple integration, and if you have some, let's say, surface x y z, and if you have three dimension, let's say dx dy dz, dx and dy and dz, and you want to change this variable dx x y z to the Cartesian, to the spherical polar coordinate, then at that time you required the Jacobian, right? So how to find the Jacobian? Let's see that thing. So Jacobian basically, so it is this thing. Okay. So now I'll start with how we can find the Jacobian for changing the variable. So this is the one application of the Jacobian. Suppose you have these two variable x and y, and this x and y of these two variables, and that is basically function of two independent variables u and v. This is the function of two independent variable x and y. Then Jacobian basically determinant, and how to find this determinant? That is del u by del u del x, del u del y, del v del x, and del v del y. So you have some, let's say, u equal to some function of x x y, and v is also some function of some, let's say, some other function g of x y, and I want to find out what is the Jacobian of these two variable, and I have to find out del u del x, in partial derivative of u with respect to x, then partial derivative of this variable with respect to another independent variable y, and the next row that will be uh, that partial derivative of this v with respect to x, and then v with respect to y. Okay, and how we can denote this Jacobian? We can denote by using the j symbol. The Jacobian will be denoted by j of uv divided by xy. Okay, j of uv and divided by j of xy, or j okay, so j of uv del of y, or this one del uv by del xy. Okay, by this way or this way we denote. Basically this matrix basically is denoted by either j of uv divided by xy. Okay, so two brackets. So this is equal to this determinant. So we have to find the determinant. So let's just take one example, then it will be much more clear. Suppose we have this data x equal to r cos theta, y equal to r sin theta. Just I already told you that we are changing that variable to Cartesian to the polar, x equal to r cos theta, y equal to sin theta. Then we have to find the Jacobian, that is basically this term del xy by del r theta. Then we have to find the determinant del of uv, del of x, del of r, right? Okay, so we have this data x equal to r cos theta, y equal to r sin theta, that is given. Now del x del r, that will be cos theta, right? We are partial derivative of these things. We are, if you differentiate this one partially with respect to r, then we'll get cos theta, because cos theta will be constant, r will be 1 with the partial derivative with respect to r, and for the y it will be sin theta, right? Then similarly with respect to theta, it will be x of, okay, so we also require the theta also. So for the theta it will be, so let's just calculate what will be theta. So it will be this one. So with respect to theta, for the first one it will be del x by del x del theta, that will be minus r of sin theta, right? And this is basically del x del theta, that is negative of r sin theta. And similarly for del r del theta, that will be r cos theta, this one, and it is already we have calculated cos theta sin theta. Now we have to find the determinant of this string, so it will be r cos square theta plus r sin square theta. Now if you take the r common, then we'll get r cos square theta plus sin square theta, that is equal to 1. So that is basically r. So Jacobian of this transformation will be equals to r. Okay. Now there is one chain rule. Okay, the chain rule of differentiation we have understand in the previous lecture. Now in this lecture we'll talked about how to find the so what is the chain rule involving in the Jacobian. Suppose you have the two variable u and v with of the function x and y, then the chain rule is del x, del u, del v and xy. Okay, so before I proceed here, so first understand this thing, that u is a function of xy, means let's say u is a function of let's say f of some xy, and v is also another function, let's say g of xy. Then in the next line it is saying that here that x and y also a function of r and s. So this x and this y, this xy, basically another function. Let's say x is another function, let's say h of rs. So f g h, let's say another function l. Okay, so y be the another function l, that is equals to l of rs. Okay, so first u is a function of xy and v is also function of g of xy, and x is another function of h of rs, and y is another function l of rs. Okay, so they are basically interlinked. Now the theorem is that the rule is of this chain rule of this Jacobian is del x del xy multiplication with this del xy del r theta equals to del uv divided by del rs. So this is basically cancel out, so only these two things is remain. Okay, so remember this one chain rule. Now from this relation we can get one corollary. What is that? Suppose we have find out the Jacobian of this term del of uv del of xy, and Jacobian of opposite, 1 by this one means del of xy and del of uv, then the product of this one will be 1, because if you put all these thing here, it is then this is also cancel out and this is also will be the same, the value will be 1. Okay, so this is one of the corollary. Now let us find out on the application of this corollary in this next example. Suppose we have the same relation that x equal to r cos theta, y equal to r sin theta, and we have to find the opposite of the Jacobian, means del of xy and del of r theta. In the last example, we have find out okay. Last example we have already found out this one, del of xy, del of r theta. Now by using the previous rule, we can easily find out this del of r theta and del of xy. Okay, just you can as you already seen that this value equal to r, so this will be of course will be 1 by r. This is nothing much, right? Also you can directly calculate this value, because this is basically equals to the determinant of del of r and divided by del of x, right, and del of r, del of y, sorry, so this is basically r, and here you have del of x, sorry, del of theta by del of x and del of theta and del y. Okay, now you can plug in all this value because you know what is r. R is basically the square root of x square plus y square, because you have to find out what is the del r by del x, right, del, and this is the del theta by, sorry for this sign, del theta del y, so on. And here similarly theta, you know, that is equal to tan inverse y by x, right? So tan inverse y by x, you can directly plug in this one and you can get the required the Jacobian. But as we already know this value is equal to r in the last example, and from the chain rule I can say that this is value equal to 1 by r. Now let's us if I solve this one, so by the previous equation I know this is equal to r. So now by using that chain rule we can know j and j dash product that is equal to 1. So that's all. Okay, thank you. See you in the next lecture.